In engineering, steady-state error is the permanent gap between a desired command and the actual physical output of a machine, remaining long after the initial transient startup effects have settled. You experience this discrepancy in everyday hardware. A vehicle's cruise control might be set to 100 kilometers per hour, yet the speedometer locks permanently at 97. Or a thermostat programmed for 25 degrees leaves the room hovering at 24.5. These persistent discrepancies have severe consequences in industrial engineering. Small variations in temperature or alignment lead to rejected manufacturing batches and mechanical failure. An automated manufacturing arm might swing rapidly toward a precise coordinate, only to halt millimeters short of its target. These errors represent a structural flaw mathematically embedded in the system's behavior. Manual tuning and calibration cannot resolve a discrepancy that is hard-coded into the control logic itself. Engineers face a paradox when designing these systems. A physical machine might lock on to a stationary target without error, yet fail to maintain accuracy against a moving one. The root of this discrepancy is the input profile. A system that maintains zero error when responding to a static step input can exhibit a large, unrecoverable error when tasked with following a constantly increasing ramp input. This behavior is a direct result of the system's mathematical architecture. The specific limits of a machine's accuracy are dictated by the internal structure of its open-loop transfer function. By identifying a single mathematical metric known as the system type, engineers can determine a physical machine's performance limitations before assembling a single component. Traditionally, calculating long-term accuracy requires solving differential equations to map out the entire time domain response of a machine. This process is complex and inefficient for rapid design. This standard block diagram for a unity feedback control system shows the physical hardware as the transfer function G of S. The summing junction generates the error signal E of S by subtracting the physical output from the desired reference input. We can isolate the transfer function of that error signal through algebraic reduction. The ratio of the error over the input is equal to 1 divided by the quantity 1 plus G of S. To find the error at infinity, we use the final value theorem, bypassing the time domain by evaluating the limit as S approaches 0. Multiplying the input signal by our error ratio provides the master equation for steady-state error. This equation demonstrates that long-term error is a function of only two variables: the physical profile of the command R of S and the design of the plant G of S. Engineers must evaluate that input term against three different physical profiles to test the machine's ability to handle increasing dynamic stress. The step input, 1 over S, commands holding a static position. The ramp input, 1 over S squared, maps to a target moving at a steady velocity. The parabolic input, 1 over S cubed, commands the system to follow a constantly accelerating target. When these three input profiles are applied to our limit equation, the S variables cancel differently, resulting in three distinct numerical constants. These are the static error constants: position, Kp, velocity, Kv, and acceleration, Ka. These denominator constants follow an inverse relationship. A larger constant results in a smaller physical error. As the physical demand shifts from holding a position to maintaining constant acceleration, the mathematical requirements for these error constants become significantly more difficult to satisfy. Whether these constants are finite or infinite depends on a hidden term in the transfer function. Focusing on the plant's transfer function denominator, the term s to the power of n reveals the system type. This exponent represents the number of poles at the origin, corresponding to the pure integrators built into the system hardware. We map system performance by plotting its type against the three physical inputs. A Type 0 system produces a finite error for position commands, but when tracking a ramp, the error becomes infinite and the target is lost. A Type 1 system uses one integrator to force the position constant to infinity, eliminating steady-state error against a static step. However, it achieves finite lag against a moving ramp and fails completely against an accelerating parabola. Pure integrators function as structural error annihilators. To track a more dynamic, aggressive target perfectly, the machine must be designed as a higher type system. We can apply this framework to determine the exact operational limits of any control loop by inspection. Consider this transfer function for a complex control loop with specific numerical values. By looking at the denominator, we see a standalone S-squared term. This identifies the hardware as a Type 2 system. Based on this structure, the position and velocity constants are both infinite. The steady-state error for both step and ramp inputs is guaranteed to be 0. The only remaining calculation is for the system's tracking vulnerability, the parabolic input, which we evaluate using the acceleration constant, Ka. In this limit, the S-squared term from the accelerating input cancels the S-squared poles at the origin of the Type 2 plant. Solving for the remaining constants reveals a finite acceleration constant of 10.4, which results in a precise steady-state error of 0.096. Identifying the system type provides a shortcut to determine where a tracking loop will fail, bypassing the need for extensive time domain calculus. This 0.096 result has specific physical meaning if this equation controlled the altitude tracking loop of an autonomous drone. With a Type 2 architecture, the drone will hold a stationary hover and execute a constant velocity climb with absolute accuracy. However, if commanded to continuously accelerate upward, it will permanently trail its intended altitude by exactly 0.096 meters. The vehicle locks into a position just inches behind the command coordinate, unable to bridge the gap during acceleration. If integrators are so effective at destroying error, we might consider building Type 3 or Type 4 systems to achieve perfection across all inputs. But integrators are destabilizing forces. Each additional pole at the origin introduces phase lag that pushes the system toward the threshold of uncontrolled, destructive oscillations. In control systems, the constant risk of physical instability.